Magnetism. So most materials have no magnetism until they are placed in a magnetic field. So sometimes when we're looking at different structures, looking at them and their structures, it doesn't look like they would have magnetism, but then when you place them in a magnetic field, whether they're repelling or attracting towards that magnetic field, displays their magnetic behavior. The presence of such a field gives us two types of magnetism, which we've already kind of discussed: paramagnetism and dimagnetism. Paramagnetism causes a substance to be attracted into the magnetic field. This usually happens with unpaired electrons. So when a substance has unpaired electrons, those unpaired electrons want to attract, and they attract when placed in an external magnetic field, giving it paramagnetism. Dimagnetism is just the opposite of that. This is when you have paired electrons. When these electrons are all paired and they're placed into an external magnetic field, they're going to repel because they don't want to be attracted towards that magnetic field. Putting that into the context of what we're going into next in this lecture, let's look at our two theories. So we have our nitrogen diatomic and oxygen diatomic. We have our Lewis structures. And then using some of the theories we've already discussed, I drew my little valence bond theory orbitals, my sigma and pi orbitals that would bond. And this shows that everything is paired. All my electrons for my nitrogen and all my electrons for my oxygen are paired. So would both of these be paramagnetic or dimagnetic? You would assume both of these are dimagnetic because they both have paired electrons, and you would think that when they're placed in an external magnetic field, they would not attract to a magnet.
Pour it all in there. Let's see what we get.
Let's look at a real-life situation. So this example up here is liquid nitrogen poured between two magnet poles. See what happens. Notice how the nitrogen is not being attracted towards the magnet. Now see what happens with liquid oxygen.
Whenever you're ready.
This is liquid oxygen being poured down a magnet. It's a little hard to see, but do you see how the liquid is actually staying attached to the magnets? That means oxygen is actually showing right there paramagnetic behavior, not dimagnetic behavior. See? It's all slowly evaporating away. However, it was attracted towards the magnetic poles where nitrogen was not. So that made sense that nitrogen was being diamagnetic, but it didn't make sense with oxygen. Magnetic susceptibility measures the force experienced by a substance in a magnetic field. Paramagnetic samples that are attracted to the magnet will appear usually heavier. We can calculate the number of unpaired electrons based on the weight. Now, the way we are looking at the magnetism is through our new theory. We know so far, here's our Lewis structure and our valence bond theory. Both of these show no unpaired electrons. They're all paired. So it doesn't make sense for them to have paramagnetic behavior. This is where molecular orbital theory comes into play. In molecular orbital theory, we apply Schrödinger's wave equation to the molecules and calculate a set of molecular orbitals. The difference here between valence bond theory is we're thinking of the molecules as a whole. Valence bond theory treats electrons as if they are just localized on atoms themselves. Molecular orbital theory accounts for the delocalization of electrons and does not assume that the electrons are in the original atomic orbitals. Instead, the atomic orbitals will combine to form new molecular orbitals. So the theory is here to help us see what the new molecular orbitals show for a structure rather than one atom on its own. The simplest guess for molecular orbital theory is the linear sum of atomic orbitals, called the linear combination of atomic orbitals. Now, this is not the same as hybridization that we've discussed before. Linear combination of atomic orbitals is a weighted linear sum of the valence atomic orbitals of the atoms in a molecule. Many of the molecular orbitals are delocalized over the entire molecule. In valence bond theory, hybrid orbitals are weighted linear sums of the valence atomic orbitals for a very particular atom, and the hybrid orbitals remain localized on that atom. So there is the difference of valence and molecular orbital theory, linear combination of atomic orbitals, and hybridization. Now, we're thinking of molecular orbitals, no more bonding. We're actually thinking of the molecules as a whole. So this happens for the s orbitals like this. Wave functions describe the behavior of an electron in an atom. This is what we've learned in chapter 7 and 8. Molecular orbitals can describe the behavior of an electron within a molecule by filling it with two electrons of opposite spins, kind of helping us dissociate the wave-like behavior. Just like an atom has more than one atomic orbital, sometimes they're empty, a molecule has more than one molecular orbital, sometimes some are empty. Molecular orbitals are combinations of atomic orbital wave functions. We've learned that we have two types of wave interferences. We have constructive interference and destructive interference. So looking at just the s orbital here, we have our two spheres right here. When they have a destructive interference, so remember when your waves are out of phase, they cancel out, right? That is an anti-bonding orbital where the electron density no longer exists. When you have waves that are in phase, they combine to form a bigger wave. That's constructive interference, and the electron density lies in the middle of the internuclear axis. This gives you bonding and anti-bonding molecular orbitals. When you have destructive interference, you will form an anti-bonding orbital. When you have constructive interference, you will form a bonding molecular orbital. Now this comes back to sigma and pi that we've learned before, but we're talking about orbitals this time, not bonds. So note here on the bottom picture, we have a 1s orbital atomic and another 1s atomic orbital. They combine, they're summed together to form a bonding orbital. Now the name that I give this is sigma 1s. Whenever you have molecular orbitals that are coming from linear atomic orbitals, all of the orbitals exist, just like when we write, for example, for carbon, right? If I write 1s2, 2s2, 2p4, when I draw you my orbital diagram, I have 1s with my 2 electrons, my 2s with my 2 electrons, and all 3 of my 2p's, even though there's only 2 electrons in it and one is completely empty. This is the same exact case for molecular orbitals. You always write bonding and anti-bonding even if they don't exist if electrons aren't available. So whenever you have a bonding orbital, you will also always write an anti-bonding orbital. So for the 1s to 1s linear combination to give us sigma 1s, we have the out-of-phase 1s and 1s to give us an anti-bonding where the node is right in the middle. There's no electron density, no probability of finding an electron for these orbitals. This is a sigma 1s star. Note how the anti-bonding is higher in energy than the atomic orbitals, and the bonding energy orbital is lower than the atomic orbital. This is because bonding has such a high chance of finding an electron and is more stable, thus lower in energy. And anti-bonding is no electron density, less stable, higher in energy. This gives us a molecular orbital diagram. So this is a hydrogen here. So you have your H atom on the left and another H atom on the right, and then H2 in the middle. The way that we kind of sum up what's happening with these molecular orbitals is through a molecular orbital energy diagram. You have the energy increasing, your atomic orbitals on the left and right side of the molecule, and then the molecular orbitals in the middle. So for H, I have 1s and 1s, one electron and another electron. I will form, for the combination of 1s and 1s, I will have a sigma 1s and a sigma 1s star. The sigma 1s will be lower in energy than my atomic orbital, and the sigma 1s star will be higher in energy than my atomic orbital. Now, all the rules that we've learned about filling in electrons and orbitals apply here. You first go to your lowest energy level. You fill an electron, spin up. Then you pair before you move to the next electron orbital. There you go. Now, what helps us in energy level diagrams is to see the stability of molecules by calculating something called bond order. Bond order is equal to 1/2 times the number of bonding electrons minus the number of antibonding electrons. The higher the bond order, the shorter the bond, the more stable structure you have. So let's calculate it here. 1/2 times number of bonding electrons. I have 2 electrons in my bonding sigma 1s minus number of antibonding electrons. I have 0. 2 divided by 2 is 1. Whenever you have a bond order that's positive, you are relatively stable. When you have a bond order that's negative or 0, it indicates that the bond does not form and the molecule is actually not very stable. You usually want a positive bond order because the electrons are more in your bonding orbitals, meaning lower in energy than the isolated atoms. And that indicates that a chemical bond is actually forming. Here's another example, helium-2. So you have your helium on the left and on the right with 2 electrons, 1s2 representing on both sides. Sigma 1s and sigma 1s star. You take 1 electron from each. This time, both the bonding and antibonding are filled. Then you calculate your bond order. Here, notice how the bond order is 0. That is not stable. Another example, helium-2 plus. So my structure is helium-2 plus. So I have a helium on both sides. Now the plus only goes to one of the atoms, not both. Since it's a diatomic of the same exact atom, it doesn't matter which one you put the plus to. In this structure, it's on the right. Plus means you're losing an electron, so you take one of the electrons away. So you fill your diagram, which means that you would take 1 electron from here, 1 electron from here, and then 1 electron from here. So 1 from each before it's paired, and then you go to the next energy level. Let's calculate the bond order for this structure. Bond order is 1/2 times the number of bonding electrons, 2, minus number of antibonding, 1. 2 minus 1 is 1, over 2 is 1/2. Now this is more stable than helium-2 because it's a bond order greater than 0 and positive. Let's look at p orbitals. Now we've talked about how the s and s come together to form a big sigma s bond and antibond. The p orbitals form 3 different types of molecular orbitals, 1 sigma and 2 pi's. The px, since x lies along the axis, they can only sum together at one spot. This will form a sigma p bond and a sigma p star bond. The 2 is only there for when it's period 2, 3, or 4, etc. Because these lie along the internuclear axis, the lobes towards the other side of the p orbitals can't interact and sum together, only the ones in the middle. That is a direct head-on collision, which is a sigma bond, representing here a sigma orbital. For the y-axis, the pi on the y, because it's a side-by-side overlap, we form a pi. We have the pi 2p bonding and the pi 2p antibonding. Where here we have our main electron density right in the middle of the nuclear axis, and then here we have a node through them where there's no electron density to be found. Last one would be the pz. Again, you have the side-by-side summation of these 2 atomic orbitals, forming pi 2p bonding and pi 2p antibonding. So for all 3 p orbitals, that are the atomic orbitals, I should say, you form the sigma p and pi p twice. Now, because this sigma is a head-on collision and you have such a likelihood, this huge density right here of finding the electrons, sigma 2p is more stable and lower in energy than pi. So when we write the distribution of the orbitals, it's a little bit different. So the way we would write it for these, excuse me, is because sigma is more stable than pi, you would have the sigma. So this was my energy diagram, the sigma 2p, and then the pi 2p. because sigma is more stable, thus lower in energy than pi. And then that antibonding as well, this never changes. Pi 2p antibonding and sigma 2p antibonding. Sigma 2p antibonding is the least stable of them all, therefore higher in energy. So, with all of that said, let's draw together the molecular orbital diagram for O2. So I draw my O2 in the middle and my 2 oxygens on the side. I have my energy, and then I have my 2s, and then my 2p, so now I form my 2s, and 2s will come together to form my sigma 2s and my sigma 2s star. The sigma 2s is a little bit higher in energy than my, well, it should be, atomic orbitals. Fill my electrons in. It doesn't really matter what order you go in. And then I have my sigma 2p, pi 2p, pi 2p star antibonding, and sigma 2p antibonding. And I fill my electrons in. So one from here, one from that one, another one here, another one here, pair it, pair. Then I have my last one from this side and my last one from this side. Alrighty, now here comes the magnetism. Notice how there's 2 unpaired electrons in the pi 2p antibonding molecular orbital. This is why oxygen has that magnetic behavior. It actually is paramagnetic. This is hard to see with the 3 other theories that we've learned so far because we're just thinking of them as bonds. Here we actually show you the electron distribution through the molecular orbitals, where the electrons are delocalized over the entire molecule rather than just one individual atom. So this is paramagnetic. Now let's calculate the bond order. 1/2 times bonding electrons 2, 4, 6, 8 minus antibonding 2, 3, 4. 8 minus 4 is 4 divided by 2 is 2, so that's very stable. Now another new term here would be to give me the configuration of the molecular orbitals. Just like we have electron configuration, we also have molecular configuration. The way we write is just KK to show you this is a molecular configuration. In parentheses, my first orbital, sigma 2s. Outside of the parentheses, I write the exponent for how many electrons I have, 2. Next, I have sigma 2s star, and I have 2 electrons. Then I have sigma 2p, and I have 2 electrons. Then I have pi 2p, and I have 4 electrons in pi 2p. Then I have pi 2p star, and I have 2 electrons. So this is paramagnetic. I've showed you my molecular orbital energy diagram. The bond order shows that it's stable, and the molecular configuration of this diagram.